Hi everyone, today we are learning about continuity of functions and one-sided limits. So specifically continuity at a point. When we think of continuity, it's really what you think it means. There's nothing being broken at a specific point. It just continues. So when we look at the definition given a function, we're going to say that a function f is continuous at a point x equals c if there's no interruptions in the graph at C. So we can also say that the graph is unbroken at C, so that means there's probably no holes, jumps, or gaps. We'll look at specific examples in a moment, so let's look at a more formal definition. A function will have discontinuity, meaning it's not continuous, at a specific point if f is not continuous at C and an interruption is occurring. So there's two types of discontinuity, which you're going to have to be able to identify. There's removable and there's non-removable. Removable discontinuity at a point C is removable if f can be made continuous by redefining what f of C is. And we'll look at visual examples of a removable discontinuity. You can think of a hole that you can fill in would be removable. A non-removable discontinuity would mean that you can't define f of C. Wherever that gap, that vertical asymptote, that jump discontinuity is, you can't fill it in. You can't redefine f of C, and it's just a non-removable discontinuity. So here's an example of a discontinuity. It's a vertical asymptote. Specifically, if we look at a function such as h of x equals f of x over g of x, a vertical asymptote occurs when the denominator equals 0. So in the past, like in pre-calc, when you guys were finding vertical asymptotes, you would set that denominator equal to 0 and find out what x values that vertical asymptote occurs. By definition, if you were to prove this, so I'm going to write this down. You guys should probably do that too. By definition, if f of x is approaching a positive or a negative infinity as x approaches C from the left or right, then we can say that x equals C is a vertical asymptote. So let's look at the picture. As x approaches 0, this function from the right is going to positive infinity, looking from the left. As x approaches 0 from the left, that needs to get out of my way, the function is going to negative infinity. And that's the vertical asymptote. Okay. Keep in mind when I was referring to this f of x, I am not referring to this function anymore. That was just a definition of a vertical asymptote in general. Okay, how about holes? Considering this function, so let's look at this function again. A hole would be a restriction of g of x that cancels out when f of x has the same root. And that's a mini pre-calc review. Now we are definitely going back to vertical asymptotes and holes and finding them algebraically. We're going to review that in this class later on when it comes to sketching. That's another chapter. So for now, just kind of know it generally, review it from pre-calc, but we'll get involved in it a little later in this course. Okay, so let's look at another couple examples. That was a vertical asymptote. That's a discontinuity. By the way, this is non-removable. There is no way to redefine that vertical asymptote. So let's look at these three examples and their discontinuities. In picture A, we have a removable discontinuity at C. There's a hole right there. However, we can redefine C to fill that hole, and therefore we call it a removable discontinuity. In B, we have a non-removable discontinuity. We have a jump right here. There's no way to redefine that. It's therefore non-removable. And in the last one, again, we can redefine C, so therefore it is removable, but it is discontinuous again. Some other terms you'll see and you'll have to use when proving discontinuities. We'll say f of C is not defined. From the left and the right, the limit as x approaches C does not exist. It's different from the left than it is from the right. We might say things like, the value at C is not equal to the limit as x approaches C. That limit is not the same as what f is defined to be. There are three things that have to occur. So a function f is continuous at C when these three conditions are met. When you show the work to proving something is continuous or not, you need to go through each one of these steps. The first thing you're going to do is check, is f of C defined? So find out what f of C is. Step 2, you're going to find the limit as x approaches C to see if it exists. And step 3, you want to make sure that this f of C is equal to the limit as x approaches C. If we remember step 3 in that last picture, did not happen. F of C was not equal to the limit as x approaches C of f of x. Okay, example 1, f of x equals 1 over x. So we're not given a specific value to decide if something is continuous at a specific point C, but when we're discussing the continuity of this, the first thing that comes to mind is, does the denominator not exist anywhere? So let's look at a value f of C. How about f of 0? Does it exist? No, it's undefined. So a final sentence for this problem, and you need this at the end, you have to have a reason every time you state discontinuity. F of x is not continuous at x equals 0 because f of 0 is undefined. All right, example 2. H of x equals this piecewise function. We want to check the behavior of continuity at 0 to make sure it's continuous. So in this case, step 1 is to check, does h of 0 exist? Does h of c exist? And in this case, it does. We're looking over here where it's equal to, less than or equal to 0, and 0 plus 1 is equal to 1. So h of c exists. We're done there. Step 2 is to check, what is the limit as x approaches c of this function, h of x? So to continue step 2, we have to check from the left and the right. The limit as x approaches, in this case, 0 from the left. We're looking at the x value being less than or equal to 0. So of x plus 1 is equal to 1. When you plug 0 in, 0 plus 1 is 1. Now the limit as x approaches 0 from the right, we're looking at the second equation here where x is greater than 0. Whoops. Of x squared plus 1 is equal to 0 squared plus 1, which is 1. So notice we have the limits from the left and right are equal, so the limit exists. H of c or h of 0 exists. They are all the same, so we can write our final conclusion for this. From the definition, it would look like this. F of c is equal to the limit as x approaches c of f of x. And in this case, specifically, we have h of 0 is equal to the limit as x approaches 0 of h of x. And therefore, the function is continuous. So h of x is continuous because, and that would be your final statement. Whoops. Okay, example 2 or 3 now. We have another piecewise function where x is not equal 1 and where x is equal to 1. Our first step to discuss the continuity is check if f of c exists. So we're looking at c equaling 1. So f of 1 in this case is just -1. No work to do there. We're looking here. Step 2, what's the limit as x approaches 1 of f of x? Well, we're looking over here. We're not looking when it equals 1, when it approaches 1. So now we can factor this out because if we plug in 1 directly, we end up with 0 over 0. So we're going to factor this to, let me erase. The limit as x approaches 1 of x minus 1 times x minus 2, all divided by x minus 1. These two cancel, so we're left with the limit as x approaches 1 of x minus 2, which is equal to -1. And now our final statement, which is step 3, f of x is continuous because f of c, or in this case f of 1, is equal to the limit as x approaches 1 of f of x. All right, another piecewise example. So I missed this, but we're going to call this function f of x is equal to the piecewise function of all 3 of those. So step 1, again, can we define c, or in this case 3? So f of 3 is equal to 5. I'm looking over here, and it exists. So now step 2, we're going to look at the limit as x approaches 3 of f of x. Does it exist? So the limit as x approaches 3 from the right, we're looking over here, of x squared minus 9 over x minus 3. So in this case, we'll have to factor the limit as x approaches 3 of x minus 3 times x plus 3 over x minus 3. These two will cancel. So we're looking at the limit as x approaches 3 from the right of x plus 3, which is equal to 6. Now, you might be thinking, okay, I'm done. F of c is not equal to the right-sided limit. But you can't do that because there are 2 ways to explain the end of this problem. You might say that the limit either doesn't exist, and that's why this function is discontinuous, or you might have to say that, looking at step 3, the limit as x approaches c of f of x is not equal to f of c. So those are 2 different reasons. So you have to continue to get there. Right now, all I have is that the right-sided limit's not equal to f of c. Now we're looking at the limit as x approaches 3 from the left. So we're looking at x squared minus 4, which in this case is equal to 5. So our final reasoning here would be f of x is not continuous at x equals 3 because the limit does not exist. Just a couple properties of continuity. So theorem 1.1, properties of continuity. If b is a real number and f and g are both continuous at a specific point c, then all 4 of these are also going to be continuous at that point. So that means the scalar multiple b times the function f would be continuous, The product of the two functions would be continuous. The sum or difference of the two functions would also be continuous. And the quotient of both functions when g is not equal to 0 would be continuous. Things to know, you don't have to write these down. Sorry if you already started. Just kind of things to keep in the back of your head, not super, super important. Okay, so we're given a function and we have to determine the discontinuity and whether it's removable or non-removable, and then we'll move on to part C and D. So here's your function. Let's go ahead and factor it to see if we have any vertical asymptotes or holes. So f of x will equal x minus 5 times x plus 5, all divided by x minus 5 times x minus 2. So here we have the x minus 5's cancel, and that means that we have a hole, at x is equal to negative 5. Sorry, positive 5. Okay. We know this is removable because we can redefine f of x at that hole. So, part C, if it's removable, what value of f of x would make this continuous? So to show this, we know that the limit as x approaches 5, because that's where the hole is, of f of x would have to equal f of 5. So in this case, the limit as x approaches 5 of x plus 5 over x minus 2 is equal to 10 over 3. And that means that we would have to define f of 5 to be 10/3 in order to make this function continuous. Okay, now we're going to look at the vertical asymptotes of this function. So we know if x equals negative 2, the denominator would be 0, and therefore the function would be undefined. And we know that when the denominator is equal to 0, that is a vertical asymptote. So to prove this, prove that x equals 2 is the vertical asymptote. So we know vertical asymptotes would mean that the limit from the left and the right are either infinity or negative infinity. So let's look at the limit as x approaches 2 from the right side. Now, if we're approaching 2 from the right, we're looking at numbers like 2.1, 2.01, 2.001. That would make the denominator very, very tiny and positive. The numerator would be 2 plus 5, which is 7. A number over a very tiny number is equal to positive infinity, or approaches positive infinity. If we look at the limit from the left of x plus 5 over x minus 2, we're looking at plugging in values like 1.999. That would make the denominator a very tiny negative number, and therefore a number over a very, very small negative would be approaching negative infinity. And therefore, we have a vertical asymptote. All right, so for this next problem, we are going to apply the definition of continuity in order to find the values of a and b that make this piecewise function continuous. Okay, so using the continuity definition, we are going to find the limit as x approaches 0. So we're looking at the first two parts of the piecewise function. And to do that, first we're going to find that first part of the definition. What is f of c? What is f of 0? F of 0 in this case is 3. Now the limit as x approaches 0 from the left is also 3. We're looking here, x being less than or equal to 0. And the limit as x approaches 0 from the right of f of x is this part right here. X being greater than 0 is from the right. So that's equal to a times 0 squared plus b, which equals b. Now, by definition, we know that the value at f of c has to equal the limit as x approaches c. So we're trying to make the piecewise function continuous, meaning these two pieces have to be equal. So we can assume now that b is just equal to 3. Moving on to the limit as x approaches 4 to connect these two. I'm going to erase a little bit real quick. So now we know b is 3 and we can use that, but let's look at f of 4. F of 4 is equal to 7, we're looking here, and that means also, because we're looking at x being greater than or equal to 4, the limit from the right is equal to 7, and the limit from the left, f of x, is right here, x being less than 4, a times 4 squared plus b, and b is 3. So now we know the limit as x approaches 4 from the left is equal to 16a plus 3. But f of x equals. Now in order to solve for a, we need to set f of c equal to the limit. So we're going to set 16a plus 3 equal to 7. And we end up with a equaling 1/4. So a equals 1/4 and b equaling 3 make this piecewise function continuous.